Hello everyone, here is another chemistry video about more fun things about electrons. So I will recommend going to watch my quantum numbers video first before this one, just because this involves the first two quantum numbers a lot and I don't want to re-talk about them all again. So let's get started. So as we know about electrons, electrons live per se in the electron cloud, which surrounds the nucleus of an atom. And electrons spread out in these energy levels. So if you remember the energy levels, there's 7 energy levels. Energy levels. There are 7 of them that range from 1 to 7. And with a max of 2n squared electrons per energy level. We also have sublevels, which are also L, and they make up the energy levels. Remember, L ranges from 0 to 3. And there are 4 L's. You have S, P, D, and F. S can have a max of 2 electrons. P can have a max of 6, D 10, and F 14, because each orbital can have a max of 1 paired electron. So this has 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. So I go more in depth in the other video, but that's a quick rundown, just so we kind of have our base point for what's going on with this. So now I'm going to talk about the rule of diagonals, which I bet you all are tired of, but it is important, sadly. That's not how you spell diagonals. Okay, pretend I spelled that right. Anyway, the rule of diagonals, it helps determine electron configuration, or how the electrons of an element fill up their energy levels. So they show the order. So there's two. Okay, let's actually just do the rule of electrons first. So this is based on the energy levels and sublevels. So every element is going to start with 1s2. So it's that first energy level, and remember, an energy level can have a max of 2n squared electrons. So since energy level 1 can have a max of 2, it's going to have 2 electrons, which is that s level, which also can only have a max of 2 electrons. So next energy level is 2s2. And then since it has 6 more spots, it's also going to have 2p6. So then you go to 3, 3s2, 3p6, and then you also have 3d10 to get it to that max number. If you go to 4, 4 has all the other ones as before. It also has the F sublevel with 14 electrons. And 5 has all of them as well. And then when you get to 6, 6 has the first 3, but it does not have the F. And that's because it just doesn't exist. There's no element with that many electrons. And so that's why 7 again only has 7s2 and 7p6. Because while these last 3 technically exist, just no element has that many electrons. So when you do this rule of diagonals, as the title kind of states, you're going to go by the diagonals. You're not going to go left to right like you're reading. So down this pyramid shape, you're going to go this way, and you're going to follow the little arrows. So when you're doing your electron configuration, this is the order that the arrows are going in that you're going to write your electrons in. So you're going to start here, you're going to go down, and you're going to go here. Then you're going to do this one, and you're going to go down. You're going to start here. You're going to go 2p, 3p, and y'all get the picture. So that is how the rule of diagonals works. So let's do a quick example. Let's do aluminum. So we're going to do the electron configuration for aluminum. So when you start, you're going to write the element symbol, and you're probably also going to want its, if it's neutral, you're going to want its atomic number so you know how many electrons you're going for. So when we start this, as the rule states, we start with 1s2, and now we have the first 2 electrons of aluminum. Well, we need 13, so we need to keep going. So we have 1s2, 2s2, which is now 4. Count the subscripts, not these coefficients. Those just tell us the energy level. So we need 2p6, 3s2. So now we're at 3p. But we only need 1 more electron to get to 13. So we're not going to put 3p6 because aluminum doesn't fill up that whole p level. It only fills up 1 more. So that would be the electron configuration for aluminum. It's just, that's the full electron configuration. So there are 2 principles that go with this rule of electrons and also the orbital filling diagram. So first there is I needed a U. There is Aufbau's principle. And Aufbau's principle states that electrons fill available orbitals of lowest energy first. So electrons are a lot like humans. They don't like to expend a lot of energy. So they're going to do whatever is easiest and takes the least amount of energy. So they're going to fill up the lowest energy levels first before they go try and fill up more. So that's why from 2p6 you're going to go to 3s2, because why are they going to try and fill up 3d10? They need 10 there. They only need 2 for the 3. So that's kind of why, that kind of explains that. There's also Hund's rule, and Hund's rule says electrons singly occupy orbitals before pairing up. So this will be important when we do our orbital filling diagrams. Okay, I will stop singing. Okay, so orbital filling diagrams. So these show electron configurations and how the actual electrons actually occupied orbitals with arrows. So let's do an example. Here we can do aluminum. So since we already done the electron configuration for aluminum, we already know what we're kind of looking for. So again, you start with the element symbol, and each orbital is going to get a little blank. So we start with 1s2. We just write 1s under there. We don't need the subscript or the exponent because that's what our arrows are going to show us. And so remember, s only has 1 orbital, and we know this s is filled up. So we're going to have an up arrow and a down arrow to show that our electrons are paired here. So next we're going to go 2s. That's going to be an up arrow and a down arrow. And now we have 2p. So remember, p has 3 orbitals, and there's 6 electrons. Now all our electrons are paired here, but due to Hund's rule, we know that they're going to singly occupy, so they're going to go up first before they come back and go down to pair up. We also have our 3s, which is full. And we have our 3p, but we only have one electron. So we're just going to put one up arrow right there. And that would be the electron filling diagram for aluminum. So, some vocab to know. Aluminum is a paramagnetic element. It has at least one unpaired electron, and that means it's weakly attracted to magnetic fields. So see, we have our one electron here. It's all by itself. It doesn't have a pair. But say if it was calcium, that would be a diamagnetic element because there'd be no unpaired electrons, and that means it's weakly repelled by the magnetic field. Okay, so that's orbital filling diagram. Another thing that electron configurations can help us figure out is valence electrons. So remember, you probably remember doing this a lot in 8th grade. Valence electrons are the electrons in the outermost energy level. That's going to be your highest N value. And these are responsible for chemical reactivity. These are the electrons when you have ions you're going to lose or gain. They're going to go into this valence electron. They're going to be valence electrons. So, we can show valence electrons with the Lewis electron dot formula. And if you were here in 8th grade, you probably remember doing this a lot. But so we're going to do it a little differently. So there's no more than 8 valence electrons. Remember, the noble gases are the ones with 8. And how you do this is you put, say, the element symbol, say there's no element X. Put the element symbol, and then you're going to show dots to show the valence electrons. But we need to show electrons how they fill up. So you could start anywhere, but so you're going to have 1 and 2 together on one side, and then you're going to displace the rest. So if you have more, 3, 4, 5, and then you can come back 6, 7, 8. So that would be how you do the valence electrons. And so say we do for aluminum. So we did the electron configuration. So we can see that its highest energy level is 3. And in that energy level, it has 3 electrons. So when we do this, you're going to have 1 dot there. And so that would be the Lewis electron dot formula for aluminum. And if you want a little cheat sheet on these, if you remember, not transition metals, you'll need to do your electron configuration, but for your tall columns on the periodic table, for the tall columns, I cannot remember how the periodic table looks today, obviously. For the tall columns, remember this has 1 valence electron, 2. I didn't draw this right, but then remember that first column with aluminum has 3, 4, 5, 6, 7, and then your noble gases, all of 8. So that's a little shorthand. And then, speaking of shorthand, I promise, this is the last thing. Speaking of shortcuts and shorthands, you have your noble gas shorthand. And this is to help with electron configurations, noble gas shorthand. So this is to help so you don't have to write all 53 electrons out. So it's used for abbreviation. So how you do this is you say you're on, we'll use this very nice periodic table I drew. When you're on the periodic table, when you want to use this, you're going to go from wherever you are, you're going to go up a row and back, remember the noble gases are in this group 18, you're going to use whatever noble gas is there, because if you notice, so say we write out the rule of diagonals, but we write it out linearly. Blah, blah, blah. Here, I'll do 4p. If you notice, besides helium, the noble gases always end on these p groups. So this is where helium is. This would be neon. This would be argon here. Oops, that's not. Oops, this would be argon here. This would be krypton. So see, they end on these p's because they. So you can use this to your advantage and use the Noble Gas Shorthand for both orbital-filling diagrams and for electron configuration. So say we want to do manganese. So manganese has 25 electrons, which wouldn't be impossible to do, but we're going to go up the row and down across. So we're going to use argon because you need less electrons than you have for this to work, or it kind of defeats the purpose. So we've already done the first 18 because we know argon is this. So now we're just going to keep going with our rule of diagonals until we get to the 25 manganese needs. So we have 4s2 and then just 3d5. And that would be, if you're allowed to use Noble Gas Shorthand, that would be the Noble Gas Shorthand for manganese. You can do the same thing with orbital fillings. You just need to write the shorthand here in the brackets and then just draw your little dashes for the rest. And this is a good review. Remember, you're going to go up before you go down. Make sure you go up before you go down. Okay, so I know this is another long video, but there's so much with electrons and I don't know the best way to break this all up. So thank you so much for watching. I hope this cleared some of it up. It's kind of hard to explain all this, but I am trying my best. Let me know, obviously, if you have any questions or anything. I'm always here to help. And yeah, I guess that's it. Thank you so much. Bye.